No, you never gonna solve that.
What?
That your nickname those three gave you.
Nice. Okay, so this says combine. Couple things that we ought to be aware of. I realize this is probably an easy question, but again, like always, you want to be careful whenever there are a bunch of negatives, especially when you've got subtraction and that sort of thing. So if we were to do this problem, we get 3x squared minus 4x minus 2y, and then I have minus 5x squared. This would be plus 7y squared minus 10y, and then plus 9. Please make sure I did all that right. Now, I've got a whole bunch of terms floating around here. I've got 7 altogether. Which ones are like terms, and how do you tell?
Same variable and exponent.
Same variable, same exponent, right? So, if I've got an x and an x and an x, okay, those are the only 3 with x's in them, but these are the only 2 that have the same exponent along with the same variable. So I'm going to put those 2 together. That's going to give me negative 2x squared. I'm going to cross those off just lightly. Let's see, kind of keeping with powers, here's the y squared. Are there any other y squareds? There's some other y's, but there are no other y squared, so I'm just going to write 7y squared. Then I've got an x here, a minus 4x. Any other plain old x's? Nope, none. Okay, so then I write that, let's see, minus 4x, cross that off. And then let's see, plain old y's. I've got a minus 2y and a minus 10y, so that's minus 12y. Cross those off, and then I've got this plain old number, this constant sitting on the end. That right there is the answer. We'll make it stick around. There we go. Okay? So, again, we tell whether or not they're like terms because they have to have the same variable and the same exponent. All right? Well, today we're going to do a section that's on operations with radicals. So we're talking adding, subtracting, multiplying, and dividing radicals. Okay, so we want to learn the rules for those. And when we start out, if we're talking about combining radicals, the rules are actually pretty similar. So if I've got 3 radical 5 plus 4 radical 5, okay, think about this in terms of what we talked about up here. Really, that's 3 times 5 to the 1/2 plus 4 times 5 to the 1/2. So if you think in terms of thinking like that's the variable, these would be the same variable and it has the same exponent. So if we're going to combine radicals, they need this. They need the same root and they need the same radicand. In other words, they need the same index, and what's underneath the radical has to be the same in both cases. So on this problem right here, I've got 3 radical 5s plus 4 radical 5s, so the answer is 7 radical 5. It's that easy. Now, if I have a problem like this, if I have 6 radical 5 minus 4 cube root of 5, the radicand is the same, but the root is not the same. Remember, the exponent that represents this one would be to the 1/2 power, and this one would be to the 1/3 power. So those are not like terms. There's nothing you can do with that one. It would have to just stay there. Okay? So let's take a look at some problems that are similar to the ones that you have on Math Excel. This is 14 fifth root of 2 minus 8 fifth root of 2. Is the radicand the same and is the root the same? It is. So I've got 14 of them, subtract 8 of them, so that's going to give me 6 fifth roots of 2. There's the answer. Again, don't get in the habit of writing square roots, not writing that index. If that's a fifth root, it's going to be wrong unless you write that in there. If you write 6 radical 2, that's the wrong answer. You got to have that correct index in there. Any questions? 6 and 6 for the radicand. Square root, square root, square root, they're all the same. So I have 1 of them plus 3 of them. That's 4 of them minus 8 of them. Negative 4 square root 6. Now take a look at the next one because this is where it starts to get interesting. These are both square roots, so they might be the same, but this is a 12 and this is a 27. So the radicands are not the same, but they're not simplified. So before you rule out the fact that hey, these aren't like terms, I can't combine these or anything, let's go ahead and simplify this. Remember, this is going to be 2 times 2 times 3. So if I take a pair of 2's out, that's going to be 10 radical 3. This is 3 times 3 times 3. Pair of 3, so if I take that out, I'd have a 3 and a 16 on the outside. That's a 48 when I multiply. And then that's the square root of 3. So even though they didn't look like they could be simplified and combined, once I simplify each one of those expressions separately, now I've got same root and same radicand, so I can add those together. I get 58 radical 3. Okay, are there any questions? Sure? Okay, let's check this one. Look at number 21. They're both cube roots, so we might be able to combine these, but let's see what we get when we simplify. Remember, if you've got a 16, that's a 2 times a 2 times a 2 times a 2. Group of 3 2s, so on the outside this is going to be a 6 and then the cube root of 2. Let's see if this ends up being something we can simplify. That's 2 times 27, which is 3 times 3 times 3. There's a group of 3. Take that on the outside. Don't forget that it is a cube root, and what's stuck underneath? A 2. So I have 6 cube root of 2 plus 3 cube root of 2. Or if we kind of set it in a way that maybe makes more sense the way we talk in English, I have 6 cube roots of 2, and then I have 3 more cube roots of 2. So altogether I have 9 cube roots of 2. So there's our answer. And then we can come across ones that have variables as well. So again, cube roots, maybe they'll be the same once we simplify them. Again, this was 27 times 2, so that's going to be a 3 cube root of 2x. Do I have any groups of 3 here? I do. I've got 3 x's, right? Actually, I have 4, but one of them is going to be stuck on the inside, so this is going to be minus x cube root of 2x. Okay, now, take a look here, please. Everybody watch. This is a common mistake. People will look at this and they'll say, gosh, these look like they ought to be the same. These look like these are like terms, and I ought to be able to combine them, but I can't add 3 and negative x together. So what we do is we take out the part that's common to both of them. So if I take out a cube root of 2x out of each one, what's left of the first one? A 3. And what's left of the second one? A minus x. Okay, and that right there is the answer. Now, if you like writing that factor at the end, okay, if you want to write 3 minus x, and then we've got a cube root of 2x here, that's totally okay. That's fine. What we're saying here is, look, I know I ought to be able to add these together. I'd get 3 minus x. I'm not sure what to do with that. Those aren't like terms, so I put those in parentheses. Okay? Any questions there? Okay? Just watch for a second. You don't have to write this down. If I did that on this problem, I could take out a cube root of 2, and I'd be left with a 6 from here and a 3 from here. So there's our 9 cube root of 2. Okay? Works the same there also. Okay, are there any questions? Okay, this one looks really ugly. But if you take a good look at it, square root on both of them, that is factored completely. This is not factored completely. This is the square root of 9 times y plus 3. And I can simplify the square root of 9. I can break this into the square root of 9 over the square root of y plus 3. So this is 3 square root of y plus 3 plus the square root of y plus 3. Questions? If I have 3 of these and I have 1 more of those, remember that's understood to be a 1, how many do I have altogether? I've got 4 of them. So my answer is 4 radical y plus 3. That's it. Any questions? Okay, let's take a look at the next ones because these are different. Okay, up here we've been doing all combining, just adding and subtracting these. Got to have the same root and the same radicand. On these problems, it's different. This is going to be multiplication and division and stuff like that. So let's take a look at this first one. Okay, if this were x times 6 minus y or something like that, everybody would just distribute, get rid of the parentheses. We're going to do the same thing here. So if I take radical 3 times 6, I get 6 radical 3, and that's normally the way I'd write it. If I have radical 3 times negative radical 3, let's kind of think of this in 2 parts. What's a positive times a negative? Negative. And what's radical 3 times radical 3? 3. Or radical 9, which is 3. And there's our answer. So we're going to do the same thing here, but again, you want to be careful with this. If you did the homework from last night, hopefully you practiced them this way. When I multiply here and here, I'm not going to write this as 2 and then radical 45, because I'm just going to have to factor 45 anyway. So what we're going to do is we're going to write 2 and then the square root of 3 times 5. Now, if you're really quick at that and don't have to write it that way, or you can write radical 45 and do that really quickly, be my guest. This is going to be minus 3 and then the square root of 3 times 2 times 2. Yeah?
Would you take out the 3's and the 2's before?
You can do it, well, on this one you can't take anything out until you get here. On this one you could simplify it. I mean, this is kind of a silly thing to write. 3 radical 4, that's the same as a 6, right? Okay? So let's finish this off. So here's what I get. Pair of 3's, that's on the outside, so that's going to be 6 radical 5. Pair of 2's, that's going to be on the outside, so that's going to be minus 6 radical 3. Are these like terms?
No.
They're not. They've got the same root, but not the same radicand, so I'm done right there. Yeah?
Why do you have a 3 times 2 times 2? 2 times 2?
There's a 3 right here.
Oh, okay.
Okay, and there's a 3 out front. Okay, this was minus 3 radical 4 times radical 3. So there's the 3, there's that 3, and there's the 4. Okay, yeah.
If you wanted to factor it completely, could you take a 6 out of that?
Sure.
Like have it 6 times square root of 5 minus square root of 3.
Yeah, if you wanted to, and you just have to check and see if it were a multiple choice question or if MathXL wants it a certain way. You could write this as 6 and then square root 5 minus square root 3. That'd be okay too. Good point. Anything else? Okay, let's take a look at the next one because this one's a little more difficult because we've got variables and a different root here. So let's take a good look. Can I simplify this one? Nope. Can I simplify this at all? I can because 81 has 4 3's in it, so I could take that out. But it's probably better in the long run. It'll probably save us writing if we just do it all in one step. So I'm going to write the cube root of 3x cubed, then minus the cube root of 81 x to the third. Right? So this is x cube root 3, a group of 3 x's. Remember, this is 3 times 3 times 3 times 3. So I've got a group of 3 3's. So I can take that on the outside, and I can also take out an x. What's stuck underneath? 3. So it's x cube root of 3 minus 3x cube root of 3. Now, if you looked at this in terms of all the rules about like terms, that variable is x, so is that one. The exponent is 1, so is that one. These are both the same root and the same radicand, so these truly are like terms. So I have one of these minus 3 of these. What should the answer be? Should be negative 2x cube root of 3. Should be negative 2 of those things there. Now, if you write it like this, if you take out the square root of 3, or excuse me, the cube root of 3, I'm left with an x minus a 3x, and that gives me my negative 2x. I don't care how you do it, just make sure you get it right. Any questions there? Hi. All right. In some sense, we treat these just like we would if they were kind of like variable expressions, kind of like we've been talking, same variable, same exponent and stuff like that. So if this were a problem with variables like x minus 2 and then it was x plus 3 or something, we'd multiply those rules together using the rules of multiplication for polynomials like this. We distribute each one of those terms through. Well, we do the same thing here. So I'm going to take the 4, and it's going to get its turn being multiplied by each one of these. Then I'm going to take the negative radical 5, and it's going to get its turn being multiplied by each one of those. And we'll see what we've got when we're left. So this is going to be 8 plus 4 radical 5 minus 2 radical 5 plus or minus? Minus, and then radical 5 times radical 5 is 5. Now, this is something interesting that happens on these problems when we're dealing especially with square roots. We're going to have a square root in the answer to this particular problem, but you'll notice that we've got a real number here and a real number there, okay? Nice integer, should say. So if I put the two of those together, I get a 3, and then I've got 4 radical 5 minus 2 radical 5. That's going to be minus, whoops, it's going to be plus, isn't it? Plus 2 radical 5. So from these two expressions, unlike with polynomials, when I multiply those normally, if I multiply two binomials, I get a trinomial. Here, I get those two terms that can be added together and those two terms that can be added together. And that usually happens. Not all the time, but usually. Depends on what the roots are. Questions? Okay, I want you to pay really close attention to this one because this one has a really unique property. Does that look familiar to anyone? What? There's not going to be a middle term because it's 3 plus radical 11 and 3 minus radical 11. That fits the pattern for difference of squares. And the cool thing is, if it's a difference of squares, both of the terms are going to have squares in them, and squares undo square roots. So if I multiply here and here, here and here, here's what I get. I get 9 minus 3 radical 11, then plus 3 radical 11, and then minus radical 11 times radical 11 is 11. So there are my 4 terms. And look, those two middle ones are the same thing. They're just opposites. And then I have 9 minus 11, so the answer to this one is negative 2. So these have a fancy name. These are called conjugates of one another. Conjugate is just a fancy way of describing a difference of squares. Okay? So if we look at this one right here, radical 10 minus radical 15, radical 10 plus radical 15. Does that fit the pattern for a difference of squares? It does. You can multiply them out the long way, or you can just realize I'm going to end up with a perfect square of this one, a perfect square of this one, and it's going to be a minus in between them. It literally is going to be a difference of 2 squares. So what do you get when you square radical 10? 10. What do you get when you square radical 15? 15. So the answer on this one is negative 5. Now, if we look at the next one, this is not a difference of squares, but it is a familiar pattern. It's not a difference of squares, but it will make a perfect trinomial square, if you want to think of it that way. So if you remember the pattern is it's going to start with a perfect square of the first one, that's 9. It's going to end with a perfect square of the second one, perfect square of radical 10, 10. And then we multiply the two of these together, that's going to be 3 radical 10, and we, help me out here, we double it, right? Okay, so that's going to be 6 radical 10. So my answer better be 19 plus 6 radical 10. Whoops. Saying 10 and writing 6. Good there? If you go through and multiply them, here's what you get. You get, oops, if you rewrite this, 3 plus radical 10, 3 plus radical 10, you get 9, 3 radical 10, 3 radical 10, and 10. Okay? And you can see those make a 19, and those make our 6 radical 10. Any questions? Okay, go ahead and flip it over. Here's what we've got to take a look at on this side. We only have 6 or 7 problems here. So again, this is what we were talking about on the previous side. We know how to factor a difference of squares. If we see a squared minus b squared, we know that's a minus b and a plus b. Those are conjugates. Those are factorings for a difference of squares. So if we're going to rationalize the denominator, remember we started learning this yesterday, but we did fairly easy problems. We want to make this denominator a nice number. So the 1's okay, it's the radical 2 that's the problem. But you can't just do this. Everybody watch please, but don't write it down. If I multiply the top and bottom by radical 2, I get 5 radical 2. When I multiply here, I get radical 2, and when I multiply here, I get minus 2. So that doesn't help me at all. I've still got an irrational number in the denominator. So what I do is I take advantage of this idea that we showed on the previous page. If I multiply by its conjugate, like we did here and here, we go from an ugly problem with a bunch of radical numbers to a plain old integer, a nice rational number. So here's what we're going to do. If the denominator is 1 minus radical 2, we're going to multiply by its conjugate, and its conjugate is 1 plus radical 2. So I multiply the top and bottom by 1 plus radical 2. Now, that is going to give me 5 plus 5 radical 2 on the top. I don't care that there's a radical there. On the bottom, I'm going to get 1 minus radical 2 squared. If I wanted to write it out completely, that's what it would look like. So I get 5 plus 5 radical 2. This is 1 minus 2. So the bottom's a negative 1. Is that all right? What would be the easiest way to write this? Yeah, the negative is on the bottom right now, so we can either leave it there, which looks a little bit silly. We can put it out front, in which case we'd have to put parentheses around this, or we can distribute it through. So again, if I put it out front, I'd have to do this. And if I distribute through, I get negative 5 minus 5 radical 2. That's probably the best way to write it. Not the only way, but probably the best way to write it. Okay, questions? Okay, let's look at the next one then. What's the conjugate? 3 minus radical 6. So if it's a plus here, its conjugate has a minus and vice versa. So this is going to be 3 minus radical 6. So let's see, I get negative 21 plus 7 radical 6. That's ugly, but it's okay. And I get a 9 minus whatever that is right there. So basically you just square the 3 and square the radical 6. It's the square of this number and whatever that radicand is. So the bottom's going to be a 3. That right there is the answer. Now, does anybody need to see those multiplied out? Just pop your hand up real quick.
Can we simplify that?
Can you simplify this? Can I cancel the 3 with the 21? No, because that's a term. Can I cancel the 3 with the 6? No, because that's not really a 6, is it? It's a radical 6. And I can't cancel terms or parts of terms. I can only cancel factors. And I can't take anything out of both of those terms, so I'm not going to be able to cancel anything off. That's it. Good question, though.
Couldn't you take a negative 7?
Okay, let's take out a negative 7. You're left with a 3 minus radical 6 over 3, right? Does that get us anywhere? Nope. Okay. Any questions? Glad you're on the ball. Okay, let's take a look at the next one. This one's kind of ugly. The denominator has 2 radicals in it. It's got a radical 2 minus a radical 5. Does that change what we do? No, it doesn't. Because even though these both have radicals, if you multiply by its conjugate, which is going to be 2 plus radical 5, sorry, radical 2 plus radical 5. Okay, now the numerator on this one, this gets to be a bit of a mess. Because I'm going to do negative 7 times radical 2 and negative 7 times radical 5. So that's negative 7 radical 2 and negative 7 radical 5. Then it's the 3's turn. I'm going to take the radical 3 and multiply it by both of those. So that's going to be a radical 6. And that's going to be a radical 15, none of which can be simplified, and none of them are like terms. Now the denominator, this is a piece of cake. Square this one and square this one. So that's going to be a, well, let's see, square that, you get a 2, square that, you get a 5. So I get a negative 3 in the denominator. Now, is that okay for an answer? Okay, mathematically it's correct. We haven't made any mistakes. Do we normally like seeing a negative in the denominator? No. No, we like to keep those as simple as possible. So again, Sliding it out front would require a set of parentheses. It would be better if we distributed it through on the top. So that's going to give us 7 radical 2 plus 7 radical 5 minus radical 6 minus radical 15. All of that's going to be over 3. Can't be simplified at all. That's it. And here's what we did there. We basically traded 3 negatives for 2 negatives, and the bottom is a prettier number. Okay, it's a little easier to work with. Okay, questions? Okay, all right. Would you do number 62, please? Do number 62. Check with your neighbor when you're done. And then we get to some interesting problems toward the end.
Okay, yeah.
Your skin's going to turn orange.
And I had an apple.
You're just one big vitamin.
The vegetable part.
What's that?
Except for the vegetable part.
Oh. And the milk. Are you drinking milk?
Yeah.
Good. This isn't bad, is it? It's a piece of cake, right? 4 plus radical 5, 4 plus radical 5. So that means my numerator is 20 plus 5 radical 5. And in the denominator I get, let's see, this is going to be 16 minus 5. So I get 20 plus 5 radical 5 over 11. Can't do anything with that. That's my answer right there. Right? Okay. This is ugly, but is it very difficult? Okay. It's about like the last one, right? So I'm going to multiply by the conjugate, radical 5 minus radical 2. The denominator on this one is going to be the easiest part of this, so let's go ahead and do that. This is going to be 5 minus 2. That's simple. Good thing on this one, it's going to be a positive 3, so that's nice. Up here we get a radical 35 minus radical 14 plus 5 minus radical 10. Now, as much as it looks like the two of these ought to be able to be combined, they don't. This is a 5 and a 7. This is a 2 and a 7. You can't take anything out. There's no way you're going to make those the same. So when we write the answer to this one, it's going to be radical 35. Whoops, keep that a minus. Minus radical 14 plus 5 minus radical 10 all over 3. And that would be it right there. Okay, are there any questions? You sure? Okay, can I slide this down? Okay, let's take a look at these last couple of problems right here. There are only 4 of them. It says, perform the indicated operation and simplify. Assume all variables represent positive real numbers. Now, why is it nice if all the variables are positive when we're dealing with radicals, in particular square roots? Tyler?
No need for absolute value.
Don't need to worry about absolute value. Okay, so let's take a look at this problem right here. This is a 10th root of a. This is a 5th root of a squared. I can't simplify this one, and I can't simplify this one. And not only that, remember that property of radicals where if they have the same root, I could do this. Like I could put them here and have like an a cubed. These aren't even the same radical. So I really can't do anything with these in radical form. But you remember I said fractions play really well with radicals, whether they're the radicand or whether they're the exponent. So let's take a look at this. What we're going to do is we're going to convert this so that we're writing this with rational exponents. In other words, fractional exponents. So if this is the 10th root, what exponent is that? 1/10. So this is a to the 1/10. If this is the 5th root, 5th root would be to the 1/5 power. So technically it would be this But then if I do power to a power, a to the 1/10 times a to the 2/5. Or you can just remember what I said when we were going over these. That's the exponent, that's the root. So that is above, that's the numerator, that's the denominator. Okay, now, still can't really do anything with this. Unless you remember how to do a problem like this. If I had x squared times x to the third, everybody here knows the answer to that. And we do exactly the same thing with this problem as we would with this problem. What do I do here with the exponents? Add them together, right? So I'd get x to the 5th. That's an easy addition problem. If I'm going to do this one, I need to figure out what is 1/10 plus 2/5. Well, that's going to be 1/10 plus 4/10, which is going to be 5/10, which I could write as 1/2. So this becomes a to the 5/10, which is a to the 1/2. Whoops, a to the 1/2. So what I've done is started out in radical form, wrote them with rational exponents, and now I'm going to go back to this. Go back to radical form. That's it. So these ugly numbers and expressions right here that don't really have much of anything to do with the square root, I mean, you wouldn't think we'd be able to simplify that at all. By changing them into rational exponents, we end up with something that's fairly nice and familiar. It's just the square root of a. Any questions? One other thing that you could do that might be easier. Has anybody seen these before? If I can find a way to make these the same, so if I wrote that as the 10th root of a, if I double the index and double the exponent, this would be a to the 4th. So this would be the 10th root of a to the 5th. I still don't have a group of 10 to take out, but if I write that as a rational exponent, it would be a to the 5/10, which is a to the 1/2. Same answer I got here, so then I could write it like this. You might find that easier than getting a common denominator. It's kind of like getting a common root. If you adjust the index, you've got to adjust the exponent on the inside. Does that make sense? Okay. All right, let's take a look at the next one. I've got a cube root and a 4th root. Again, the trick is going to be b to the 4/3, b to the 3/4. What do I need to do with the exponents? Add those together. So this is going to be b to the, well, let's see, 3/4, 4/3.
16/12.
Okay, so I'm going to use 12. So that's going to be 16/12 plus 9/12. Is that right? So I end up with b to the, let's see, that would be the 25/12. So this is going to be the 12th root of b to the 25th. I'm looking for groups of how many? Groups of 12. I've got 25 b's. How many groups of 12 do I have? I've got 2 groups of 12. So that's going to be b squared on the outside. Please make sure you write the correct index there. How many b's are stuck on the inside? Only 1. So there's the answer right there. Okay, I'm not going to finish this problem this way, but how could I change both of those so they were the same root? What's the smallest root I could use that both of those would go into? 12. So if I make this a 12th root, if I multiply this one by 4, I've got to multiply that one by 4. There's to the 16th. If I make this one a 12, I multiplied that by 3, so that would have to be to the 9th. It's the same idea. Either way you want to do it is fine. They both have their advantages. That works really well here. Okay, let's see if it works down here. Already got one doubter. Let's see if it actually works. Okay, this would be x to the 2/3, and this would be x to the 1/5. Now, if I had x to the 7th over x squared, my answer is x to the 5th, because I subtract the bottom exponent from the top exponent, right? So the answer on this problem ought to be x to the 2/3 minus 1/5. Got to get a common denominator here. 15. So 10 fifteenths minus 3 fifteenths. Whoops. 7 fifteenths. So that would be the 15th root of x to the 7th. And can that be simplified at all? It can't. Should we check and see if that other little technique works? No? You could make those both 15s. This would be a 15, that would be a 10, that would be a 15, that would be a 3. Okay? Then you can put them underneath the same radical. It'll work. Okay? All right. Any questions? Okay. I'm going to do this one that way. So I need those both to be the same root. So this is going to be the 15th root of, let's see, I multiplied that by 3, so this is going to be a to the 12th, b to the 3rd. Need a 15th root times the index by 3, so I'm also going to times the exponents by, 5. Multiply those by 5, so that would be a to the 5th, b to the 5th. Good there? That is the 15th root of a to the 12th, b to the 3rd over a to the 5th, b to the 5th. Is that all right? So that's going to be the 15th root of a to the 7th, b to the 2nd. 15th root of a to the 7th, 15th root of b to the 2nd. Okay? This is a tough problem. You could write it with rational exponents like that if you want. Okay? Can I do anything with this?
Well, you can
Rationalize it.
Very good. Rationalize. I'm looking for groups of how many? 15. How many b's do I have? 2. How many more do I need? I need 13 of them. So I'm going to multiply by a 15th root of b to the 13th, a 15th root of b to the 13th. So here's what I get. What's on the bottom? A b, because I've got 15 of them now, right? And on the top, a 15th root of a to the 7th, b to the 13th. So again, we go from something that looks really awful and doesn't look like we can use any of the properties, but by either thinking about them in this way or changing the index so it's the same by adjusting the index and the exponents, we get something we can simplify. Okay? Any questions? Okay. What are we doing tomorrow? Q&A with a worksheet that reviews the first 5 sections of this chapter. When is the next test? A week from tomorrow. Okay, a week from tomorrow. We've got 3 sections we'll cover next week. We'll have a review day and then test. Okay, go ahead and get working on the homework assignment, please. Hopefully you were done with 7.3 and 7.4. Okay, so you can just plow away at 7.5. Yep, you were supposed to do both. Yesterday was 7.3 and